Hello all, my name is Dan O'Brien. Today's talk is on the rise of computer vision in Agritech. I'm lucky to work in the AWS startup team in Australia and New Zealand. And we're seeing a lot of great Agritech startups from this region take on big global challenges. Like many Kiwis, I have deep family links to farming, sheep farming in my case, where 5 generations ago, Edward Elworthy moved to South Canterbury in 1864. I have also spent much time in France, and that's why I don't have your typical Kiwi accent. Australia and New Zealand, and France for that matter, have a long-standing heritage in agriculture, a heritage which has never shied away from innovation. From the first ever frozen meat shipment to London in 1882, or electric fences from the 1930s, to the data-driven dairy cows of today. And this is set only to continue in a world of digitally enabled agriculture, which promises not only to improve yields, but also reduce our impact on the environment. And if there's one takeaway message from this talk, it is this: give it a go. It's a great time to experiment. It's easy, it's simple, and you can try it out quickly. We'll take a look at, first, AWS agriculture customers and trends, then innovative computer vision use cases. Finally, Yorka will dive deep into edge computer vision. Everything we do at Amazon starts with the customer, and I wanted to highlight this New Zealand Agritech customer to start, Halter. Here we see a photo of Halter CEO Craig Piggott with a dairy cow, with a sort of Fitbit for cow or halter around its neck. With a halter, a farmer can get a full suite of herd, pasture, and animal data on his or her phone. What is the condition of the animal? And at a herd level too, where are the cows? Should they be moved? And quite amazingly, with the actual smartphone, you can automate herd movements and save up to 20 to 40 hours per week. How does this magic work? The collar sends cues such as warning sounds and vibrations to guide the herd to, say, a different paddock or milking shed. This is the future of farming, a farm without fences. I thought this was science fiction when I first heard about it. Halter was born on AWS. AWS allowed them to focus their engineering talent on core business instead of managing infrastructure. But stepping back, we know the challenges are great. Food systems today are just not fit for purpose. You may be familiar with some of these daunting statistics. Our world population is expected to hit nearly 10 billion by 2050 from about 8 billion today. Agriculture already consumes 70% of our freshwater resources, 50% of arable land, and contributes 24% of all greenhouse gas emissions. That's globally. For local context, almost half of New Zealand's greenhouse gas emissions come from agriculture. In Australia, agriculture contributes around 15% of greenhouse gas emissions each year. Humanity must learn how to do more with less. And consumers are conscious of this and are making purchasing decisions accordingly. We're seeing some major themes develop to address these challenges. The first is total control. That is controlled environment agriculture. Sensors everywhere to measure growth rate, water uptake, transpiration, shape, number, reaction to light. Vertical farms use as much as 90% less water and 80% less labor and no pesticides, but can use more energy, which produces more emissions, and only available for certain crops, of course. The second theme is the robot revolution. This is things like drones for monitoring and spraying, data gathering tractor trailers, self-driving tractors, swarms of robots working together. Tractors even today have app stores, a real sign of the times. The third is precision agriculture. This is the end of spray and pray. It means precisely applying the right inputs based upon data. We will see individualized and unit-level health and yield information. Also, the frequency of data capture will change from manual and frequent observations to automatic, real-time, and insights need to be gleaned from the data quickly, too. Well, many people are concerned about the rise of tech in agriculture, and it is an important topic to discuss, but the ecological versus technological divide is somewhat of an illusion. In fact, organic farms produce between 20 and 50% less food than larger, more scaled farms when evaluating environmental impact per kilogram of food. So it isn't a case of back to nature or forward to high tech. It is about getting the best of both worlds with a systems thinking approach. Now, moving on to the AWS cloud and agriculture, just for a moment. AWS offers reliable, scalable, cost-effective cloud computing services. And when we think about agriculture and the AWS cloud, a few points are quite relevant. Elasticity is one. Seasonal activities like harvests might drive demand for your service. Likewise, you might not be paid until after the activity. The AWS cloud is elastic, and you only pay for what you use. Connectivity is important in agriculture. One must plan for situations with limited or no connectivity. The concept of edge compute comes into play. By edge, we mean the edge node in a network, being able to function with or without a connection. More on the edge later in this session. Finally, I wanted to touch on sustainability. Many in agriculture want to leave the world a better place than we found it. Farmers need the latest knowledge, insights, and technology to help with this. Moving to customers using AWS. This is just a small sample of our customers. It is a very diverse group across the agriculture, value chain, and broader food system. From working with these customers, we have developed a perspective regarding themes that are important. Our customers are sending strong signals around edge inference, data enrichment, traceability, and genomics as use cases they want to develop. But where is the data in agriculture? Humor me for a moment. Close your eyes and imagine holding a handful of soil in the palm of your hands. In one handful, there's information about soil type, nutrients, moisture, and microbes, all which tell a story about the optimal seed genetics for that ground. If we widen our lens to the field, this includes data regarding crop spacing, pest and disease pressure, irrigation, weather, yields, and satellite, as well as in-field imagery. And if we zoom out even further, there's data to be collected regarding storage, transportation, logistics, equipment maintenance, and animal health, food processing, and cold chain management. Agriculture is a data-rich industry with a wealth of information that can provide actionable insights for optimizing operations throughout the food system. So the question is, how can this data be captured and staged and enriched to develop sustainable agricultural solutions? Open your eyes and let's talk about vision. So we often talked to customers with prompting questions like the one you see on the screen here. If you could capture visual information, what problems could you solve in agriculture? Let's talk to some agricultural computer vision customer examples now that touch upon dairy, horticulture, viticulture, apiculture, and conservation. Here's an example. We infer a lot from a simple picture like this. Even if we're not experts, how many pigs are moving into the facility? We don't want to double count the pigs. I count 6 about. Are the pigs young or old? They look young. Do they look healthy? Yes. What is their color? Pink. What direction are the pigs walking in? They're walking towards me. Well, computers have to be trained to see these same patterns. And this is how I often think about computer vision. It's just about seeing patterns. In this case, we'd need to take into account the direction that the piglets are walking in. And so we would train the computer vision model with bounding boxes around the heads of the pigs to get an indication of direction and to avoid double counting pigs. On to dairy. This is Ireland-based Agritech startup Agritech. They're using computer vision in dairy to help with questions such as, how do we get better data for farmers about their livestock? We all need data. Good data to improve genetics, improve efficiencies, but most importantly, we need to think about improving animal welfare. Cows are stoic animals, which means they have evolved to not show lameness. It helped their ancestors and relatives survive in the wild. Also, as an industry, alternative proteins are competing for consumer attention these days. So the sector needs to demonstrate that animals are well cared for and well looked after. So founder Terry Canning and the team at Agritech took on just this challenge. They set up cameras at the entrance and exit points of a milking parlor. The cameras pull the footage up to the AWS cloud, run computer vision models on the footage, and derive specific insights to the farmers, like a mobility score, lameness levels, and more. And with this, Agritech directs farmers to treat animals that are lame. The animal is happier and produces more milk. They were able to get the first prototypes going within a week with AWS. And this slide shows how they did it, using AWS services like building blocks to build a simple data pipeline with different stages. The image data moves through these different stages, from ingress to analysis to insights, and finally onto the application where farmers can see the results. A simple, effective architecture for machine vision. I'll put references to these examples at the end of the presentation. Moving on to a horticulture example. One of the challenges here is it is expensive to accurately size and color fruits such as apples, and sample sizes can be small. The size and color are important for the way apples are processed down the supply chain. Is this apple suitable for a supermarket, for instance? So New Zealand-based Agritech startup Hector developed a computer vision model to help called Spectre. Spectre estimates the size distribution of an apple bin in real time using AWS from an iPhone or iPad. The two most useful points of information for apple growers are mean size and standard deviation. The mean is the average apple size, while standard deviation gives an indication of the variation in the top layer of the bin. Spectre can then estimate the size for the entire bin accurately. This reduces time by 90% on average for this process and increases sample size by over 100 times. And Spectre has scaled on AWS to scan and detect over 20 million pieces of fruit in less than a year. Hector's technology is now used in 11 countries, including the United States, Spain, and South Africa today. Moving on to another horticulture example now. One of the biggest problems that growers face is to have visibility on their crop at all times. Founders Fiona Turner and Aaron Elkington at Australian Agritech startup Bitwise Agronomy took on this challenge. They built automated crop analysis using computer vision to give growers operational insight into their crops. It's called GreenView. Growers purchase a standard GoPro camera, attach them to their machinery, and capture side-on imagery as they go about their usual farming activities like mowing and mulching. This is uploaded then to their GreenView environment, run through neural networks to give actionable insights on operational tasks and yields back to the customers. One such customer is Mike Casey at Forest Lodge Cherry Orchard in central Otago. Mike is producing New Zealand's first zero-emissions food under the NZ Zero brand. Mike used GreenView to not only estimate crops and detect early signs of disease, but also to get a God's eye view of their cherry orchard performance. I think many farmers would appreciate a God's eye view of their operation. Moving on to a sector and produce that is very dear to my heart, wine. My French connection's coming through here. Grapes need constant care and attention, so startup Cropsy asked, why are less than 1% of vines monitored? Today, processes to estimate yields, locate these disease clusters, optimize inputs are manual and error-prone. Cropsy took on these challenges and developed unique hardware that lets growers monitor every single plant. Cropsy used computer vision analysis via camera, which could be mounted on a tractor and record data as it traveled along each row. They liken it to gaining the insight of 1,000 eyes and can now care down to the individual plant. Growers can now see a map of disease clusters, fruit counts, dying or missing plants, and optimize the application of inputs to care for their vineyards. They've used Amazon SageMaker and deployed their models on the edge on the cameras. We'll talk about Amazon SageMaker a bit later on. On to a conservation example now, with a twist. This one involves audio. New Zealand's national bird, the kiwi, is a threatened species. There are only about 68,000 kiwis left, and they're disappearing at a rate of about 20 per week. As part of their kiwi monitoring program, the Department of Conservation in New Zealand placed microphones in the Fiordland National Park across almost 1 million hectares of forest. The recordings created a huge amount of data, 2,000 hours of audio. It would have taken 12 straight weeks, morning and night, for scientists just to listen to it all. On top of this, identifying kiwi calls is incredibly difficult with background noise from the forest. So the department engaged consulting firm Curious, an AWS partner, and their data scientists to transform the unstructured audio files provided by the department into visual spectrograms. First step, get good training data. Scientists tagged a sample of the data manually as Kiwi or non-Kiwi to train a computer vision model using AWS. Second step, build a model. They've used a pre-built image classification algorithm available in Amazon SageMaker to do this. Third step, test the results. The tool can now automatically convert recordings into spectrograms and find Kiwi sounds within them and notify scientists when a sound is found. Moving on to another conservation-related case study, let's talk about Israel-based Beewise. They provide robotic homes to save bees. 71% of all fruit, vegetable, seeds, and nuts are pollinated by bees worldwide. This includes everyday's foodstuffs like tomatoes, cucumbers, avocados, and more. Even your morning coffee. However, bee populations are declining, with some colonies facing complete collapse. Between 30 and 40% of bees die every year worldwide, across regions, across the globe. Why is this happening? Well, researchers are still working on it. Climate change, diseases, pests, beekeeping practices, and other factors are being considered. At the same time, beekeepers are not able to monitor and treat hives at scale in real time. They might get out to the hive once every few weeks, driving a few hours into the field. So what if beekeepers could not only remotely check the health of their hives in real time, is this hive looking healthy, but also fix problems remotely? Apply this pesticide, for example. This is computer vision and robotics applied to a traditional industry. Beewise's hives, called bee homes, help beekeepers monitor their colonies from afar. Bee homes can flag diseases, pests, hunger, and more, and ping beekeepers in an app when a poor condition is discovered. Beewise designed their frame scanning and image processing architecture, leveraging a range of AWS services in a data pipeline. Speed to market was essential, so they made uses of services like Amazon S3 buckets to store images, AWS Lambda, our serverless functions, to trigger the computer vision process when an image lands in a bucket, Amazon SageMaker to build, train, and deploy the computer vision model at scale, and Beewise has reduced the average bee mortality rate to less than 10% in their bee homes from about 35%. It's a great example of AI being applied to quite a traditional industry to not only improve yields hugely, but to do good for the environment. We'll keep a reference to this architecture at the end of the presentation. We're going to dive further into this technology with Yorka in a moment and show edge computer vision, how that can be quickly experimented with. But stepping back a few minutes, we've seen how very different use cases of computer vision across agriculture are being applied. From different corners of the globe, computer vision is being used from aquaculture to viticulture, and it's becoming ubiquitous, a bit like GPS and location data has become. Computer vision helps automate tasks and save time in quite traditional industries. And agriculture is but one industry of many that is leveraging this new digital technology. Manufacturing, energy, mining, automotive, and other sectors are benefiting too. Your sector can benefit too from this. And our AWS for Industrial initiative can help accelerate benefits to your customers' experiences through technology such as Internet of Things, artificial intelligence, and machine learning. Have a go. It's a great time to experiment. It's easy, it's simple, and you can try it out quickly. Without further ado, let's dive deeper now into the technology. With Yorka, over to you.
Thanks, Dan. So many novel applications using computer vision. And to hear that cows prefer to be milked by robots, that's utterly amazing. I'm Yorka, a solution architect, and I'm privileged to be working as part of the startup team here at AWS. My background is in software engineering and networking. I've been a CTO and co-founder of a startup, and by day I like to work shoulder to shoulder with our startup CTOs, and by night I love to explore building things. Today I'm going to talk about services on the edge with AWS and how you can easily, quickly, cheaply build and deploy computer vision solutions. But first, you may be thinking, what does he mean by the edge? And how is that important to computer vision? Well, let me explain it through the evolution of networking and define an edge in the context of how we see it now. What you see on the screen there are diagrams from research into communication networks from the 1960s, introducing the concept of distributed networks. This is a great way to show where edge applies with the cloud. On the left, you have a hub and spoke, the client to the edge connecting to a server in a data center, and the data center being that nexus of communication forming the basis of the economics of the cloud. With a centralized approach, you get specialization at the core. It allows customization and amortization of the cost of physical hardware, the cost of networking, and the cost of security and scaling. And this is where the inescapable economics of scale apply. And that's why AWS can provide such a broad range of services and you only pay for what you use. We've seen more differentiation in networks with the expansion of the centralized model, introducing more decentralized models into the cloud. The concept of availability zones, a discrete logical data center, and when connected in a close geographic area, forming a region. In this case, the edge is the availability zone. Now there is growth in distributed architecture, moving the edge into devices that are physically located closer to what is serving over the network. Usually small devices that provide some onboard compute capacity and are connected back to decentralized networks. These edge nodes are tailored to specific use cases. As an example is devices and sensors in the field that capture data. Right, I get it. Edges are everywhere. So when I'm building, how do I choose which is best? Not so long ago, everything used to be on the edge. I had my computer under my desk, and now I've just moved everything to the cloud. And you're saying we have to move everything back to the edge? In reality, it's a hybrid of the edge and how we use the best of both of these. Starting with the cloud, centralized economies of scale, as mentioned earlier, you don't have to maintain hardware, scale up and down very easily for compute-intensive workloads such as machine learning training. It's easy to manage. It's the complexity of services are becoming more and more managed at an increasing level, introducing levels of abstraction, reducing the undifferentiated heavy lifting you have to do. On the edge, distributed localization. A piece of hardware is designed for that workload, and the cost of the devices that provide accelerated computing is dropping, and their power is increasing. It's also very low latency at the edge, which is important in use cases such as autonomous driving. And for some workloads, such as computer vision, you reduce by an order of magnitude the amount of data you send over the wire for inferencing workloads. So in short, cloud is easy and powerful, edge is cheap and fast. The real power you get is a blend. To understand the range of services AWS has and what I like to call the spectrum of edginess, we can arrange them from edgy to cloud. Starting from the left, right on the edge, the Internet of Things, IoT things. FreeRTOS, a real-time operating system for IoT devices moving across to IoT Core for connectivity and management. We have SageMaker Neo for building machine learning models for edge devices. From there we have a range of data transfer and some local compute with the Snow family, a collection of ruggedized devices from AWS. Then we have non-traditional cloud extensions, Outposts, Storage Gateway, File Gateway, EKS, ECS Anywhere, where you run workloads outside of a cloud data center, but still are well connected to the cloud in a distributed manner. Right on the edge of the cloud we have local zones, Wavelength, CloudFront, Lambda at Edge, Direct Connect, all designed to bring edge compute back to those distributed and centralized locations. To show how quick and easy, cheap, and accessible computer vision is on the edge, we've built this project to demonstrate going from a freshly unboxed NVIDIA Jetson Nano with an off-the-shelf USB camera to a working computer vision system in less than 10 minutes. This of course excludes the time it takes to train a simple model using SageMaker. It's as easy as unboxing the Nano, running a shell script to install the libraries, and downloading the trained model capturing the images for inference. This is a high-level architecture of how this fits together. Once unboxed and started, the service is working on an edge device via an SSH connection. The user can send images via a simple post to an API gateway, and this will trigger a training job, first using AWS Fargate to process the images and videos, and then triggering an Amazon SageMaker job, finally compiling the model using SageMaker Neo and storing it in Amazon S3. All the heavy lifting here is done in the cloud for fast and accessible compute. The user starts the inference where the model is downloaded to that edge device, loaded into the Neo deep learning runtime, and processes the image stream from the camera with local inference. So let's get into it. First, let's take a look at my setup. We're actually viewing this through the world of an edge device running an image classifier. Here the Jetson Nano in a developer kit straight out of the box. I've added a USB web camera, added a Wi-Fi card, and added a nice case for appearance sake. I've installed the latest Jetson Nano developer image, including Jetpack SDK, onto an SD card and connected it to my network. And that's the hardware, just a bill of materials of just under 400 Australian dollars. As you can see by moving my two cows around, the image classifier is telling us the cow breed based on what it sees or infers. It's inferencing. In this case, I've only briefly trained my model on Herefords and Friesians, and it's primarily based on the colour that it sees. To get started, what I need to tell the Jetson is what I want it to detect. I've captured a few short videos of my friends here that I've uploaded to Amazon S3. I then trigger an AWS step function via a REST request via API gateway, and I'm just telling the step function the location of the videos and which cow is in the video. This will then chop up the videos into images, send them onto a training job using Amazon SageMaker and using the built-in image classifier algorithm. The resulting trained model is finally compiled using SageMaker Neo, targeting the ARM architecture of the Jetson. When complete, it just runs a script on the Jetson to download and install the needed dependencies, such as the SageMaker Neo deep learning runtime and the compiled model, and then we start inferencing. Once you've downloaded the model to the device, all the inferencing is local and does not need an internet connection. Lots of heavy lifting, helped by automation in the cloud. All this extraction and training is dependent on the size of the videos. However, in my case, with the two 30-second videos, this was completed in 8 minutes. Once you've proven your computer vision use case, it's time to productionize and scale. One key service that helps is FreeRTOS, an open source real-time operating system for IoT devices. AWS is committed to FreeRTOS, and it includes the kernel and software libraries that make it easy to securely connect your small, low-powered devices to more powerful edge devices, and gateways running AWS Greengrass or AWS Cloud Services like AWS IoT Core. This is one of the ways we support development at the edge. The next key service is AWS IoT Greengrass. This makes it easy to connect your devices to the edge. It used to be quite challenging to deploy and update your edge devices, and AWS IoT Greengrass embeds local Lambda compute, local messaging, local device shadows, and Greengrass ML inference brings the management of machine learning right to the edge. Now, AWS has a number of computer vision services. High-level APIs such as Amazon recognition for inference and labeling images. This is great to get started quickly in the cloud. For edge use cases, you'll need to be well connected and on a fast connection. Amazon SageMaker Ground Truth, for automatic labeling and human-in-the-loop labeling. This helps you better train your models in the cloud. Amazon SageMaker Neo for compiling specific machine learning models for edge device deployment, as you've seen earlier. On the industrial side, we have AWS Panorama, Amazon Lookout for Vision, and Amazon Monitron that cater for industrial use cases where you have a high number of users, bespoke hardware, and specific industry needs. So why should we care about computer vision? Well, if I haven't convinced you yet, here are some numbers and some more reasons. The market is growing and forecast to grow to $13 billion by 2023. Camera technology is continually improving and the cost is decreasing. Low power usage, low bandwidth is becoming ubiquitous with LoRa and Zigbee, making it easy to connect in remote locations. Model training and inference costs are decreasing, and using technologies like SageMaker, Spot, Inferentia, Elastic Inference, just to name a few, drastically reduce the cost of experimentation and moving to production. Edge compute hardware, such as NVIDIA Jetson, Coral Edge, and Raspberry Pis, are decreasing in cost and improving access to accelerated chips well suited for computer vision. Finally, model management is just getting easier, using services such as SageMaker, Edge, Manager, Studio, and Debugger. To continue your cloud journey, please use these training resources. In closing, if you have any further questions or feedback, we'd like to invite you to join us at the AWS Startup Loft. In our loft, you can connect one-on-one with the AWS startup team in Australia and New Zealand, such as myself and Dan, plus technical and business startup events, workshops, and more. I'll see you there. We really value your feedback to help us improve our sessions, so please share your out of 5 rating, and thanks for watching.